All right, let's talk about one of the most powerful, most elegant, and frankly, one of the weirdest ideas in all of computing. We're talking about the fork system call. It's this concept that's right at the heart of operating systems like Linux and Mac OS. And once you get it, it's like you've unlocked a secret level to understanding how computers really work. So let's jump right in.
So it all really starts with this one big question. Have you ever wondered how a single program can do multiple things at once? Think about your web browser, right? It's downloading a file, but you can still browse other tabs, or your music player shuffling songs while you're building a playlist. How does it juggle all that? Well, in a lot of cases, the answer comes down to the star of our show today, fork.
Okay, before we dive any deeper, let's get one thing straight right away, because it's the #1 point of confusion. You're always going to hear fork mentioned with its partner in crime, exec. But the difference between them, it's actually beautifully simple. Think of it this way. Fork is the command to clone myself, just make a perfect copy. Exec, on the other hand, is the command to become someone else. It completely transforms, replacing itself with a whole new program. So clone and then become someone else. That's the key idea. Hang on to that.
All right, so here's what we've got on tap. We're going to start with what the fork call actually is. Then we'll look at that classic duo, fork plus exec. After that, we'll check out some of fork's surprising solo acts. Then, things get a little weird with zombies, orphans, and bombs. We'll figure out how to clean up after children. And finally, we'll ask the big question, why does fork still endure? So let's kick things off. What exactly is the fork call? Well, at its absolute core, it is all about cloning. The best analogy is probably biological cell division. Seriously. One moment you've got one cell, and then boom, the next moment there are two nearly identical copies. They each have their own life now, but they share the exact same history right up to that point of division. Now, to really get what's being cloned, we first have to talk about what a process is. And here's the thing. A process isn't the program itself. It's not the file for Chrome sitting on your hard drive. No. The source material calls it an engine of execution, which is a great way to put it. It's the live running instance of that program. Think of it like a container that's holding all the memory, all the resources, everything that program needs to actually do its job. And that brings us right to the official definition. See, fork is what's known as a system call, and that's really just a fancy way of saying it's how a program asks the operating system, the boss, to do some special powerful task for it. And in this case, that task is to create a brand new process by duplicating itself. And we have names for these. The original is the parent, and the new copy is, you guessed it, the child.
Okay, and here's where the real magic happens. This is the part that bends your brain a little. You have two identical processes. So how on earth do they know which one is the parent and which is the child? The whole trick is in what the fork call returns. Get this, you make one call, but it returns twice, once in each process. In the parent, fork gives back the process ID, or PID, of the new child it just created. But in the child process, it just gets back a 0. That one single difference is everything. It's the signal that tells each process, okay, you're the parent, do this, or you're the child, do that.
All right, so now let's see how this awesome cloning power gets used in the most common pattern you're ever going to see out there. We're talking about the classic fork and exec duo. This isn't some abstract concept, it is the exact mechanism your command line shell uses to run pretty much every single command you type.
So, picture this. You're sitting at your terminal. You type ls to list your files, and you hit enter. Right now, your shell, let's say it's bash, and its process ID is 501, is just sitting there, waiting for you to tell it what to do.
Okay, so bash needs to run the ls program for you. But it's got a problem, right? It can't just become ls. If it did that, it wouldn't be a shell anymore, and your command prompt would just disappear. So what's the solution? You know it. It calls fork.
And just like that, poof, suddenly there are two bash processes running. You've got the original parent, PID 501, and a brand new child, we'll say it got PID 888. And for this one brief moment in time, they are identical clones of each other. Both of them are shells ready to go.
But they don't stay twins for long. The child process, which knows it's the child because fork gave it that 0 return value, it has a new purpose in life. It immediately calls exec and basically tells the operating system, hey, I'm done being a shell. Scrap all this, replace me completely with the ls program.
And this is the final brilliant step. The operating system does exactly that. It just wipes the child's memory and loads the ls program right in its place. So that process, PID 888, is no longer a bash clone. It is ls.
It does its job, lists your files, and then it exits. And all the while, the parent shell, good old PID 501, was just waiting patiently for it to finish, ready for your next command. That's the whole dance.
But fork isn't just a one-trick pony that sets the stage for exec. Not at all. It has some really powerful solo acts that are absolutely fundamental to how things like web servers and background services work.
So, for example, take a web server. It gets an incoming connection from a user, and what does it do? It can fork a child process whose only job is to handle that one user's request. This is huge because it lets the parent server immediately go back to listening for more connections. That's how it handles tons of users in parallel. And here's another cool trick: demonizing. A process can fork and then the parent just exits immediately. This leaves the child running all by itself in the background, totally detached from your terminal. It's perfect for those services that you need to have running all the time.
Now, this power to create new life, so to speak, it comes with some serious responsibility. If you don't manage these parent-child relationships correctly, you can end up with some pretty spooky things haunting your system. We're talking about zombies, orphans, and even bombs.
So let's break down the two ghostly figures you hear about the most. First up, a zombie process. This is a child that has already finished its job and died, but its parent is still alive and just hasn't gotten around to acknowledging the death. It's not running or using CPU, but it's still taking up a slot in the system's process table, kind of like a ghost. Then you have an orphan process. This is the exact opposite. The parent has died, but the child is still alive and kicking. Thankfully, the system doesn't just let them wander around. These orphans get adopted by a special process called init, which basically becomes their foster parent and makes sure they're cleaned out properly when they're done.
And then there's the truly nasty one, the fork bomb. This is just a tiny, vicious piece of code with one purpose: call fork in an infinite loop. Each new child immediately does the same thing, which creates this massive exponential explosion of processes. It happens so fast, it just eats up every last bit of memory and CPU, grinding the entire system to a complete halt. It's a pretty stark reminder of how a simple tool can be incredibly dangerous.
So, the big question is, how do we avoid unleashing a zombie apocalypse on our own systems? Well, it all comes down to being a responsible parent process. And luckily, the operating system gives you a whole toolkit to do just that.
The most straightforward way is to use the wait system call. The parent basically says, "I'm going to take a nap," and the OS puts it to sleep until one of its children finishes. As soon as that happens, the parent wakes up, collects the child's final status, and poof, the zombie is properly laid to rest. Now, a more advanced way is to use something called a signal handler. The parent can tell the OS, "Look, don't put me to sleep. Instead, just tap me on the shoulder. Send me a signal whenever a child is done." That signal then triggers a little bit of code to do the cleanup, which means the parent can keep doing its main job without being interrupted.
So you might be thinking, after all this time, with all the fancy new stuff we have like threads and async programming, why is this simple old fork call still so important? Why does it endure? The answer really is all about the philosophy behind it.
There's this quote from the source material that just nails it. The use of fork and exec exemplifies the spirit of Unix in that it provides a very simple way to start new tasks. And that's it, right there. The whole Unix philosophy is about making simple tools that do one thing and do it well. Fork does one thing. It clones. Exec does one thing. It transforms. And when you put those two simple building blocks together, you get this incredibly powerful, flexible, and surprisingly easy to understand way to handle, well, everything from running a command to managing multiple users at once. It all just boils down to this one beautiful two-step pattern: clone, then specialize. First, you make a perfect copy of your current world. Then, that copy changes itself to take on a new specific job. It's an idea that is so simple and yet so profoundly powerful.
And that really leaves us with one last thing to think about. This core idea, clone, then specialize, it's so fundamental that it didn't just stop with fork. Where else do you see this pattern in computing today? I mean, think about it. How do we launch virtual machines from a template? How does a Docker container start from a base image and then run a specific command? The spirit of fork, it's everywhere.